world of Lie theory and some related results in spectral geometry. Go away, Siri. I have this big problem with Siri, which is yeah, great. I say K-theory a lot because I'm a K-theorist, and Siri is sure that what I'm really saying is, hey, you know who. So sorry about that. Anyway, so I'll try and show you what this hypoelliptic Laplacian is, this family of operators is. I'll try and explain what it does, and most importantly, I'll try and explain how it does what it does. There are many aspects to this, and I'm certainly going to give a sort of one-sided presentation, and you'd hear something quite different from Jean-Michel himself, I'm sure. If you're anxious to see all of the details, then you have to be prepared to suffer through a rather heavy dose of analysis. There's a lot of heavy lifting in the background, which I'm going to suppress in this talk, except maybe here and there where I'll explain where you need it. So we're going to try and emphasize as much as possible geometric ideas and some very simple matrix algebra ideas, which Jean-Michel discovered. They're really new instances of phenomena in supersymmetry and in supersymmetric matrix algebra, which probably deserve more attention than they get when they're buried amongst hundreds of pages of analysis. So my job is to not talk about the analysis and instead try and talk about some of the algebra and maybe some of the geometry. All right, so as not to leave you in too much suspense, here is the hypoelliptic Laplacian in at least one case. This is the case of a circle. There are hypoelliptic Laplacians on manifolds, on complex manifolds, on symmetric spaces, compact groups. The same idea has many manifestations, but in this talk, I'll mostly be talking about compact groups, and in particular, mostly about the circle. And here's what it is. The hypoelliptic Laplacian is this family of operators parameterized by some positive number b. And the first thing you notice about this operator is that it's not an operator of this family of operators, is that they're not operators on the circle because they act on functions of two variables, an x and a y variable. So x here stands for the variable on the circle. I can think of the circle as R modulo z, but y is just another real variable. So what this thing is acting on is the circle times the real line, functions on the circle times the real line, and it's obviously acting on vector valued functions, not on scalar functions. And you should think of the vectors on which it acts as being Z2 graded. We'll get to that in due course. So that's what this thing is, and if you know anything about differential operators at all, you'll see immediately that this is not a friend, a close friend from the world of index theory. This is not an elliptic operator on the cylinder, the circle times the line, because ellipticity means it's an isotropy condition, isn't it? It means that the operator somehow differentiates with equal strength in all directions, and that's obviously not the case here. It's second order in the vertical y direction, and then it only differentiates in this particular direction with order 1, according to the vector field y ddx. So it's a sort of strange operator. Also, it's not self-adjoint, which means that any kind of spectral theory for this operator is fraught with difficulty. Anything you want to say about this operator requires you to pay a price in analysis before you can say it properly. All right, nevertheless, that's what it is. As for the word hypoelliptic, you probably know this, but let's just dispense with it anyway. It just means that the operator has the property that all of its all solutions to equations with a smooth unknown are smooth. So if PF is smooth over some region U, then F itself has to be smooth over the region U. And these operators caught the attention of Homander back in the 1960s, perhaps. And he proved a famous theorem that if you have a family of vector fields on some manifold, some open subset of Rn, it's just a local result. And if the Lie algebra they generate under Lie bracket spans each tangent space, then this sums of squares operator, which is mostly second order, but it has this first order term x0, and then I tacked on an order 0 term, which is just a function. Any operator which looks like this is hypoelliptic. It's kind of important that the coefficients here are not concerning H, but concerning the vector fields, the coefficients are real. Different things happen over the complex numbers, but this is Homander's theorem. And it's going to guarantee that all of the operators we're going to be examining will indeed be hypoelliptic. As for the property of hypoellipticity, it's not terribly useful by itself, but it's usually proved by obtaining some estimates, some Sobolev space estimates for the operator P. And it's that slightly stronger set of results, some subelliptic estimates for P, which are in the analytic background of everything that's going to happen here. Hypoellipticity isn't quite enough to get you going, but the estimates which Homander and others used to prove hypoellipticity are what you need. Anyway, so this applies to our operator L, the one that we saw on the previous page. And it's significant that it also applies to the heat operator. So that now if you add one more variable, a time variable, and you look at the operator whose solutions would be solutions to some L heat equation, it too is hypoelliptic. And that means, for instance, that the fundamental solutions of the heat operator are smooth functions away from the source. That kind of smoothness will play a role in what's coming. All right, what are you supposed to do with hypoelliptic Laplacian? Well, this is the first formula of the theory, I guess, and so this is what I'm going to focus on mostly. And you can see it's a sort of Selberg type formula in red. On the one hand, the eigenvalues of the Laplace operator on the circle, I mean, just d squared dx squared. And on the right are closed geodesics on the circle. Well, they're also not very complicated, are they? And we have this interesting and non-trivial identity. Of course, the geodesics and the spectral values are both integers, but they're not the same integers, especially on a circle whose circumference is not 1. And you can note particularly the way that the time parameter t appears here, t times lambda squared on the right and 1 over t on the left. Okay, having said that, it's not a complicated formula. It's a special case of the Poisson summation formula. It's a theta function identity. So you can get this very, very easily. And what we shall have to endure to learn how Bismut does this is quite a lot. So I'm not, I mean, that you want to keep that in mind, that this is quite a complicated machine, which here I'm going to use to prove something extremely simple. But at a certain point, things turn around, and as the complexity of a problem increases, what tends to happen is that Bismut's method doesn't get much more complicated at all. It's a total pain in the neck. It's a real struggle to put enough machinery in place to handle the case of a circle. But if you manage to do that, then handling the case of just about any of the other applications that Bismut considers, it's not much more difficult. And you get formulas, and the interesting thing is that the formulas, as they appear, as they are presented by Bismut's method, they're not the same formulas. They're equivalent formulas to the ones you see coming from, for example, harmonic analysis, but they're not the same. And so now you have two different formulas for the same thing, and that's a lot of where the interest in this and potential importance lies.
Can I ask, so at the end of the day, are you going to, or is Bismut going to interpolate between the two sides of the formula?
Yeah, there's going to be so that, let me just go back to this formula. We're going to study the operators LB, and we're going to take the limit as B goes to 0 and somehow associate the left-hand side of this red formula with the limit of LB as B goes to 0. And we're going to associate the right-hand side with the limit of LB as B goes to infinity. There's a lot more to be said, and well, I have a lot more slides, so I'll try and say them as time goes on. Okay, just a little bit of background before I give you another hint about what Bismut's up to. This is just basic stuff that I'm sure you're all familiar with. Thanks to Hilbert, we know that if you look at the Laplace operator on a closed Riemannian manifold, then you can diagonalize this thing completely on L2 functions on M. That's what Hilbert did in integral equations. So you can find an orthonormal basis of eigenvectors, Fn. And using those eigenvectors, you can construct an interesting collection of operators, a one-parameter semigroup of operators, which solves the heat equation. So that if you apply to an initial u, e to the minus t delta, then you get some ut, and that solves the heat equation like I've indicated here. And it's not difficult to see that each of these exponential operators, e to the minus t delta, is actually an integral operator, and it's not difficult to write down an explicit formula for the integral kernel. So that's what's written near the bottom. So I'll write my integral kernels in this way. I'll write the operator and then p comma q. That's the integral kernel k of pq for the operator e to the minus t delta. And it's just given by this standard formula. And that means that if you take the trace of this operator in the sense of operator theory, the sum of the diagonal entries in a matrix representation, first of all, that's the same thing as integrating the integral kernel down the diagonal. This was Hilbert's idea that the integral kernel is a sort of continuous version of a matrix. And what you get, as you can easily see from the formula, what you get is just the sum of the eigenvalues, or the sum of the exponentials of the eigenvalues. So you can access the spectrum from the trace of e to the minus t delta. That's the idea here. And since around the 1930s or 40s, this has been the principal way, the principal method of spectral geometry to understand, attempt to understand what the spectrum of a Riemannian manifold is through this heat semigroup. Okay. And as t goes to 0, it's rather easy to understand what happens to e to the minus t delta. It just converges in the sense of operator theory to the orthogonal projection onto the kernel of delta. That's just because e to the minus t lambda, for any positive lambda, converges to 0 as t goes to infinity. Maybe I said t goes to 0 by accident, but I meant t goes to infinity. On the other hand, the large time asymptotics, or excuse me, the small time asymptotics of this heat semigroup are rather more intricate. And the way you understand them is as follows. You want to imagine taking the manifold on which the operator acts and just rescaling it and making it much bigger by a factor of t, or the square root of t, I guess. And once you've done that, the t times the Laplace operator on the original manifold is the same thing as the Laplace operator on the scaled manifold. And as t goes to 0, these scaled manifolds flatten out, don't they? They become closer and closer near any point to just the tangent space of M at that point. And one obtains, with a bit of analysis, asymptotic formulas which relate the integral kernel of the heat operators on the one hand, on a curved manifold M, to the same integral kernels on the final flat manifold, which is the tangent space of M. I put in red a scalar factor, which is t to the minus n over 2, and that inevitably pops up here. And the reason it pops up is that the integral kernel isn't really it's not really a function, it's a type of density. And so when you pay attention to the measures which are floating around, you see that you don't get pointwise convergence of integral kernels on these manifolds MT. As t goes to 0, you have to add in a scale factor. Okay, but the scale factor is good, not bad. It's a feature in a way, not a bug, because from this formula here, it's very easy, for example, to understand why Weyl's asymptotic law for eigenvalues is true. Okay, one more slide of just background information, and then we'll get back to, or maybe 1.5 more slides, and then we'll get back to the operator of Bismut. This is the supertrace of a 2x2 matrix, maybe whose entries are operators, not numbers. And because of the sign, this guy vanishes not on commutators, but on supercommutators. And this is the sort of thing that you see in the world of the Dirac operator. If your Laplace operator is actually the square of a Dirac operator, then something very interesting happens. And if you replace the trace by a supertrace, then this trace, now a supertrace, which is a function of t, is actually a constant function of t. And the reason is, if you differentiate it with respect to t, the derivative of the supertrace is the supertrace you can calculate of a supercommutator, and therefore it's 0. And that's the essence of the McCain-Singer method in index theory. One now wants to apply this formula and evaluate the supertrace in the limit as t goes to 0 and in the limit as t goes to infinity separately, and get some interesting formula. As t goes to infinity, you get the index of d, and on the other hand, as t goes to 0, well, Getzler discovered a remarkable thing, that if you rescale the manifold, but at the same time you rescale the spinors on the manifold in a clever way, then in fact there's a convergence of the operators t delta to some limit operator, just like there was on the previous slide in Weyl's law. There's some limit operator that I'm calling omega here. And when you apply supertraces, there is no longer any divergence in t like there was before. Some red, the red annoying factor, t to the minus n over 2, actually just disappears here. And you get an exact formula for the limit, not an asymptotic law for the limit. When I say little supertrace, little str, what I mean is that this integral kernel is no longer scalar valued, it's 2 by 2 matrix valued. So you're calculating the supertrace of the integral kernel at each individual point. And of course, very famously, Ezra proved the local index theorem this way, gave an extraordinarily beautiful proof of the local index theorem this way, because you can identify exactly what this operator omega is, and you can calculate its integral kernel, especially at this easy point 0, 0. And so the integrand here is some very explicit thing. It's the A-roof form of Atirin-Singer. Okay, we'll see all of these things in some strange new context in a moment, if I manage to stay on schedule. Let me just say, give a few slides indicating maybe a little more honestly or accurately what Bismut's work is all about. It's not about circles. It's not even about compact groups. It achieves its grandeur, if you like, in the context of locally symmetric spaces. And a more realistic indication of what it's capable of is Selberg's trace formula, which is a similar thing to what we saw earlier, the Poisson summation formula relating lengths of geodesics to eigenvalues of the Laplacian. Here's the formula that Selberg proved in the case of a compact closed hyperbolic surface with some transcendental functions which look suspiciously like the ones you see in index theory, this A-roof function x over sine, hyperbolic sine of x, for instance, and a few other things. This, from Bismut's point of view, actually from Selberg's point of view as well, this formula comes about in the following way. You take the hyperbolic surface and you uniformize it. You think of it as its universal cover as being exactly the hyperbolic plane. And then it's a simple matter to connect the integral kernel for the surface S for the heat operators with the integral kernel for the heat operator on the hyperbolic plane, which is something you can actually calculate explicitly. And so this formula in red is a simple matter, not complicated at all. And so let's see what we're supposed to do in order to calculate the trace of e to the minus t delta s, which is the sum of e to the minus t lambdas for the surface S. You need to integrate the left-hand side of what I've written in red over the manifold. So that's the same thing as integrating the right-hand side over a fundamental domain. The big P that I've written is a point in the hyperbolic plane, which maps down to the little p, which is a point in S. So on the one hand, you're integrating over a fundamental domain. On the other hand, you're summing over gamma, and when the dust settles, you obtain an interesting and quite practical formula for what the trace of e to the minus t delta s is. It's given by this sum now over conjugacy classes, and there are some easy to calculate volume terms which are unimportant, and then some terms which are called orbital integrals, these trace gammas, which involve the integral kernel for h, for the heat operator for h, for the hyperbolic plane. That's easy to understand. But now you have to integrate that integral kernel essentially over a conjugacy class in the group G. That's less easy to understand. But if you can understand it, then you've figured out a formula for the trace of e to the minus t delta s. And this is what Bismut does as far as Lie theory is concerned. He calculates orbital integrals which look exactly like this. These are orbital integrals always for semi-simple elements in the group gamma, which is why we're working with a compact surface here. So just to give you a reasonable sense of what these formulas look like, here's what the formula is of Bismut in the case of SL2R. And I've chosen the world's simplest conjugacy class. Amazingly, Bismut's work doesn't degenerate when you choose the conjugacy class just to be the identity element, the one element conjugacy class. Even though you're only integrating over a single point, still you get something rather interesting. And this is Bismut's formula. This is a non-trivial formula. And it's the simplest non-trivial instance of the types of formulas that Bismut has provided. And you can compare this with formulas from the world of Harishchandra, because you can equally well attack these problems from the perspective of representation theory, which is how one does in general attack the Selberg trace formula, or how Selberg would attack the Selberg trace formula. And what's involved is another integral and some standard data from representation theory. There's the famous Plancherel measure. There's the spherical dual, which is the part of the unitary dual of a group which contributes to the decomposition of L2 of the hyperbolic plane, or L2 of G mod K, into irreducibles. And then attached to each representation, there's some Gaussian term, e to the minus t infinitesimal character squared. All right, so this is what Harish Chandra would say is the answer to the problem of calculating this integral kernel. And you'll notice right away that these are not one and the same formula. I guess that's not totally clear because I didn't write down what the Plancherel measure is, but the Plancherel measure is some tempered function, so it's not going to affect the fact that in one integrand there's e to the minus t times something, and in the other integrand there's e to the minus something divided by t. So these two formulas are interestingly different, and this is just the most simple case that you might consider of a potential application of Bismut's work to the world of representation theory. There's a whole suite of formulas, and they cover, in the end, not just the spherical dual, but all of the dual, and understanding how the two are related to one another is really a fascinating enterprise, and there are some very interesting computations done already by Shushen and Yanli Song and Shang Tan. So I think we'll probably be hearing more from these people in the future about their discoveries. And so it's interesting what goes on, and it's more or less true, not exactly true, but more or less true that in theory, you're actually calculating the Plancherel formula by calculating these orbital integrals. So Bismut is somehow actually doing that in principle and more or less. So that, I hope, gives you
Can I just ask a quick question about the previous slide? This is
sure.
Ezra.
Hello, Ezra. Yeah.
Hi. I'm just looking at the power of T. So, of course, SL2 is three-dimensional, but I'm having difficulty kind of working out why that power of T and what the behavior actually as T goes to 0 of the right-hand side is. Is there anything to be said, or you'd rather just ignore my question, which is fine?
So that one of I was going to say something which is a little bit different, which is the behavior of this integral as t goes to infinity turns out to be maybe a more compelling issue to study than t goes to 0. 3 is the dimension of, t is indeed the dimension, sorry, 3 is indeed the dimension of SL2R, and it's 3 divided by 2 because it's always n divided by 2. So I would say it's t to the minus 3 over 2 for the same reason it's always t to the minus 3 over 2 for the heat asymptotics of a three-dimensional manifold.
It's just that the integrand doesn't look to me as if it is bounded below as t goes to 0, but maybe I'm misreading it.
The integral is going to go as t to the 1/2, isn't it?
I'll leave that to you to determine. Of course. Yes. Thank you very much. That's what I said was involved a certain amount of rubbish because we're on the hyperbolic plane, not on SL3, which is two-dimensional, not 3.
Yeah,
then now I'm fine. Okay, thank you.
Okay, so having bumbled about, we were rescued, and okay, good. Thank you, both of you. All right, here we are. Now back to the hypoelliptic Laplacian after that extremely brief tour through applications and potential applications. I'm going to focus on the circle, which is unambiguously of dimension 1. And I'm also going to make its circumference 1, just to keep everything as simple as possible. And I'm going to explain how you build this LB. First of all, what the bits are that you build it out of, which are the Dirac operator on the circle, and the harmonic oscillator on the line, or the usual square root of the harmonic oscillator. It's not obvious how you take these bits and you build them into a useful hypoelliptic Laplacian. If you remember the formula, you'll probably agree with that right away. And then hopefully I'll have time to explain the rest of the story, which has a lot to do with understanding this limit as t goes to infinity. So here's the Dirac operator. on the circle. So Bismut chooses it to act not on spinors, but on differential forms. So you should always imagine that the Dirac operators that we'll be studying are acting on differential forms, which makes D a 2x2 matrix of operators in the case of a circle. In the case of a Lie group or a compact group, in fact, any reductive group, the Dirac operator is chosen to act again on the exterior algebra of the Lie algebra. And Bismut chooses Costin's cubic Dirac operator for a reason that I'll explain later. So in the non-compact case, this is not an elliptic operator, and that adds all sorts of other interest to the problem. Anyway, for this particular operator, when you square it, you get the Casimir operator of the Lie algebra plus a scalar, and that is what's important for later on. Finally, Bismut uses a skewer joint version of the Dirac operator, not a sulfur joint, but I just felt it was more convenient here to use a sulfur joint operator, and so I'll have to add some square roots of -1 later to compensate for the choice I made here. And on a line, here is the quantum harmonic oscillator, whose spectral theory is completely well known. And it's also known how to take a Dirac type square root of this quantum harmonic oscillator, which I've written down in red in the middle of the screen. And it too acts on the exterior algebra of, well, in this case of R. There's a general version of this operator which acts on any vector space of dimension n, and then Q acts on the exterior algebra on vector valued functions where the vectors lie in the exterior algebra of that vector space. We have an operator D, which is a 2x2 matrix, and an operator Q, which is a 2x2 matrix. And now we're going to try and stick them together. And there's a standard way to do this in index theory, which mirrors the way that Laplace operators work on manifolds. If you want to multiply two manifolds together, if you do multiply two manifolds together, then, so to speak, the Laplace operators add. The Laplacian of a product of two manifolds is, in a certain sense, the sum of the two Laplacians, with one of them acting, of course, on the first factor and the other one acting on the second factor. And from the early days in index theory, people figured out how to do exactly the same thing for Dirac operators, these square roots rather than the operators themselves. And it's really close to just taking the sum of D1 and D2, with D1 acting on M1 and D2 acting on M2, except there are some signs which you strategically add. You use graded tensor products, if you like, and not usual tensor products. So there are a few signs, and they're stuck in there, so you get these nice formulas at the end. I'll call this the Kasparov product because I come from the world of Kasparov theory. This Kasparov product, when you square it, you just get the sum of squares of D1 and D2. And if you're interested in index theory, this thing is designed so that the index of the Kasparov product is the product of the indices. Okay. This is an ancient construction in K theory to begin with, but Kasparov made good progress understanding this from many different points of view. All right, now, so one of the things we can do with the two operators that we have at hand is take their Kasparov product, D with Q. In fact, I'm going to stick in a parameter T and take the Kasparov product of D with big T times Q, like you see at the top. And so it acts on functions on the cylinder, but the functions are valued in 4 vectors, 2 vectors tensor 2 vectors. And the reason that you stick in the T is what's described in this theorem here, which is a very easy theorem, that if you take the limit as T, big T, goes to infinity, having fixed a little t, then the entire heat semigroup for the Kasparov product actually converges to the heat semigroup for the original operator T. So it's a fact that the supertrace of the left-hand side is the product of indices, and it's a fact that the index of Q is 1. So it's a fact that the supertrace of the left-hand side is always equal to the supertrace of the right-hand side. But in fact, there's a refinement of that, which is you can make the left-hand side actually converge to the right-hand side at the level of operators just by introducing this factor T. And the proof is very, very easy. Nothing complicated is going on. How do you actually compare these two operators, the Kasparov product on the one hand and D itself on the other hand, which live on different spaces? Well, you can embed the space on which D acts, which is just the forms on the circle, into this space of forms of some kind on T times R, just as exactly as the kernel of Q. Because anything in the kernel of Q is a function on the cylinder, which is exactly Gaussian in the y direction, so its y behavior is prescribed. And also it has to be degree 0, just a function, so to speak, according to the second exterior algebra family. So the kernel identifies with L2 functions on the circle with values in one copy of the exterior algebra. So you can fit the Hilbert space on which D lives into the Hilbert space on which the Kasparov product lives, and get this, as I say, interesting refinement of an index formula, which you see at the bottom of the slide. This is what Bismut did for a living for many years, is to refine this very naive and simple argument in many beautiful ways for the service of index theory.
I have a quick question about the, sorry, Nigel, about the previous slide. On the right-hand side, do you mean tensored with an idempotent of rank 1? Sort of in the vertical direction. It's not actually, the reason I was confused is the left-hand side are compact operators, and literally speaking, what you wrote on the right-hand side isn't a compact operator. So
that's correct. What I mean by the right-hand side in this formula, maybe I don't know if I want to even risk this, but okay, let's just do it, is, yeah, indeed, this operator, the first operator acts on the kernel of Q, and it's e to the minus d squared once you identify the kernel with the domain of the Dirac operator, L2 of T, with coefficients in lambda. And then it's just, you add a big 0. So that would be a more accurate representation of the theorem. But I shall commit the crime of avoiding adding the Dirac sum of 0 again. So prepare yourself. Okay, so here's an operator. I'm sure something like this might have happened must have happened in Bismut's subconscious, although he denies following this particular route to invent his operator. But let's just imagine taking the two exterior algebras and multiplying them together. After all, why not? It's an algebra. To obtain a more efficient space in which it's just exterior algebra valued functions on a cylinder, rather than functions valued in tensor product of two exterior algebras. It must be tempting surely it's tempting to think about building an improved Kasparov product here. And the first thing you might think of is just to take the sum, d plus t times q, just as an experiment. And what happens, it's sort of interesting what happens if you do this. Because now when you square the new fake Kasparov product, you don't get d squared plus t squared q squared anymore, because there's a cross term which doesn't go away, and instead something rather beautiful happens. And what you get from the cross term is exactly y times d dx. So it's an operator on the cylinder, a vector field on the cylinder, which of course is exactly the geodesic flow on the cylinder. So that's interesting, and it's a little bit of progress maybe towards the goal that we're trying to head towards. But what about the formula that we were just discussing, having to do with convergence to e to the minus td squared? Can you still recover e to the minus td squared from this new Kasparov product? It's interesting what happens. It doesn't look so good to begin with, because you do a little bit of a calculation. I said before that you can identify the Hilbert space on which D lives with the kernel of Q. And that doesn't quite work here. In fact, it couldn't work worse from a certain point of view, because if you apply D to a function in the kernel of Q, you actually get a function which is orthogonal to the kernel of Q. So it's exactly the opposite of what you might hope for. And that's just a consequence of the Z2 gradings. On the other hand, D squared does preserve the kernel of Q, so all is not lost. And so let's just see what happens. Let's do a little experiment here. I want to take d plus tq squared. I want to exponentiate it to e to the minus t, d plus t2q squared, and I want to understand whether or not in the limit as big T goes to infinity, I get e to the minus td squared in the sense that we saw before. And so I'm breaking up the Hilbert space on which my test operator is defined according to the kernel of Q and the orthogonal complement of the kernel of Q, the functions which are just Gaussian in the vertical direction and degree 0, and the functions which are not. So this is not a decomposition with respect to the Z2 grading. It's just a Hilbert space direct sum decomposition. Now we have to do a little calculus, relatively simple, at least at the level of precision that I'm going to do it here. We want to understand e to the minus, as I've written, d plus big T q squared. Okay, fine. How are we going to do that? Well, let me use this Cauchy integral formula and represent it as a contour integral in which the integrand is a resolvent operator. Now it becomes important to understand what these resolvent operators are. And so you do the math and you see that they're given by block 2x2 matrices exactly as I've indicated here. Differences, I guess, of block 2x2 matrices. Okay, so what do we, and now we have to take the inverse of this matrix to plug into the Cauchy integral formula. So let's see what happens if you take the inverse of this rather messy 2x2 matrix in the middle of the screen. Well, if you take a 2x2 matrix, there's actually a formula for the inverse of any 2x2 matrix, whether or not the entries are scalar. There are several formulas, but the one I'm interested in here is a formula which works when the 2-2 entry of the matrix is an invertible operator. In that case, you can factorize any 2x2 matrix A, B, C, D in the way I've indicated. And because now you have an upper triangular and a diagonal and a lower triangular matrix, it's easy to figure out what the inverse is. You just invert each term and reverse the order. And what you find by multiplying those matrices out is that the 1-1 entry, the top entry, the entry corresponding to the kernel of Q, is of the inverse of mu minus d plus tq squared, is given by E inverse, whatever E inverse is in this particular case. So you have to figure out A, little b, little d inverse, and C, and you have to plug them into the formula for E, and then you have to see what you get. Well, what do you get? Here's what you get, just doing that algebra, and it's kind of interesting what happens here. If you look at the fraction in the middle, the numerator is t squared q squared, and the leading term of the denominator is also t squared q squared, and the other terms are small compared to the leading term. And q squared is invertible on the orthogonal complement of its kernel. So as t goes to infinity, that fraction in the middle converges to the identity. And so E converges to mu minus d squared plus d squared. And the operator d and d squared, they all disappear. And so you're not seeing in this 1-1 entry anything resembling the operator d. Instead, you're seeing 0, or rather in this particular case, mu. So when you plug that discovery back into the formula, the contour integral, which tells you what the exponential is, what you find out is that for large t, this exponential doesn't represent or resemble in the 1-1 position. It doesn't resemble e to the minus d squared at all. It resembles the identity operator. And then there are 3 other terms which I didn't tell you about, but they resemble 0 in the same sense. So that's a bit disappointing. On the other hand, the way in which everything went wrong and we ended up with 0 or e to the minus 0, which is the identity, is easy to analyze. It came from this formula, I just went back a slide, in which we had minus d squared plus d squared. And you can totally eliminate the problem by the artifice of taking d plus tq squared and subtracting d squared from it. And if you do that and you repeat the argument, then what you find is that e to the minus d plus tq squared minus d squared does indeed converge to e to the minus d squared. This little element e that we were discussing on the previous page, it really does converge to mu plus d squared on the kernel of Q. And the other entries in the inverse matrix really do converge to 0. Let me try and digest that a little bit. There's an annoying minus sign, which I forgot to mention on the previous slide. We didn't get mu minus d squared, we got mu plus d squared. And in order to cope with that, let's make a small adjustment with the square root of -1. This is why Bismut starts out with a skewer joint Dirac operator from the beginning. If you form this operator and you calculate what it is, first of all, you'll find it's a hypoelliptic operator, and you do the analysis, you'll find that it indeed is possible to exponentiate this, and the result is a trace class operator. And now this operator has the right property when you let the t go to infinity, big T go to infinity. The exponential of e to the minus t L of t is just e to the minus d squared on the kernel of Q. And you can take the supertraces and you'll get an identity of supertraces. Now the remarkable thing is that the supertrace on the left just becomes a trace because the kernel of Q is entirely concentrated in degree 0. And so the limit of supertraces on the right is actually just a trace on the left. And you're taking the Dirac operator squared and you're restricting it to the kernel of Q. And in this case, that's just the 0 forms on, identifies with the 0 forms on M. So we're just looking at the Casimir operator acting on functions. That's a remarkable discovery of Bismut. And it comes down to some new features of matrix algebra, which nobody saw before. Okay. So we can access the trace, not the supertrace, the trace of e to the minus Casimir operator, e to the minus Laplacian, through a supertrace if we pay the price of studying this LT. So what is this LT operator? Well, if Bismut uses 1 over b instead of t, that's his parameter. He also divides by 2. And so his hypoelliptic Laplacian is basically the one I was just mentioning, but in actuality, it's what's written in red, and that's exactly the operator that we started our discussion with. And the formula I've given is the correct formula for any compact group using Constant's Dirac operator. For non-compact groups, if you're working on the symmetric space G mod K, there's an additional important detail which I won't go into right now, in fact, at all in this lecture. Okay, so we've sort of reverse engineered, if you like, an explanation for why the hypoelliptic Laplacian is the way it is. It's from this point, from the point of view of this lecture, it's designed expressly with the purpose that as b goes to 0, the limit of the supertrace of e to the minus TLB is the trace of e to the minus t times the Laplacian, or t times the restriction. I said the restriction of d to 0 forms. I should have said the restriction of d squared to 0 forms. Can I do this with that? There we go. All right. And the remarkable fact is, and the opportunity for proving interesting formulas comes from the second result here, which is that the supertrace is actually independent, not of t, but of b. If you differentiate the supertrace of e to the minus TLB squared with respect to b, then you get 0, because when you work it out, the derivative, again, is a supercommutator. And so the trace of any supercommutator being 0, the derivative is equal to 0. To make this work, you really need to know that d squared commutes with q. And that's not particularly inconsequential requirement, because remember that the coefficients of d and the coefficients of q are borrowed from the same algebra of endomorphisms of the vector space lambda. So to make them commute, you really have to arrange that d squared is truly a scalar operator, so you don't have to worry about the coefficients of d squared, so to speak, tripping up with the coefficients of q. And that's why Constant's operator comes in. And it's obvious now, I believe, what needs to be done. On the one hand, we've designed the hypoelliptic Laplacian so that item 1 on this slide is true, so that the limit to the supertrace as b goes to 0. B goes to 0 is somehow like the large time limit back in the world of index theory, because remember, the parameter was 1 over b, not really b. Anyway, we've designed things so that the limit as b goes to 0 of the supertrace is this spectral quantity, the trace of e to the minus t delta over 2. In other words, basically the sum of e to the minus t lambda, where lambdas are the spectrum of the Laplacian. And by good fortune, thanks to the discovery of Constant of this special version of the Dirac operator, actually the supertrace is b independent. And so if you can calculate a limit as b goes to infinity of the same supertrace, I mean, really it's constant, but you know what I mean. If you can exploit the large b behavior of LBs somehow to evaluate the limit in a different way, then you'll have a formula. That's what Bismut is all about. And when you go in the limit as b goes to infinity, it's not about spectral theory and matrices anymore. It's about geometry. And the final thing I want to do in the lecture is try and describe 2 or 3 of the steps which are involved there. It's no longer relevant for this final part of the argument, or not very relevant, to work with supersymmetric operators acting on differential forms. It's much simpler to just work with scalar operators. And so now LB will stand for just this scalar version of the hypoelliptic Laplacian. It's the same operator that appeared in the official hypoelliptic Laplacian, except there was some additional terms related to the number operator on differential forms, which I've suppressed in this picture. It's a different L. I used an italic L, but it took me a while. I mean, I wrote these damn slides, but it took me a while to notice that I'd used a different L. Anyway, so we're talking about scalar operators for a little while, and I want to explain some of the geometric features of this operator. First of all, by explaining what goes on for a much simpler operator, which you see is related to the scalar operator above. And this is called Kolmogorov's operator. It's was studied by Kolmogorov in the context of probability theory back in the 30s. And so let me just make one simple slide to tell you something about how solutions of the heat equation work if the heat operator if the Laplacian is replaced by this Kolmogorov Laplacian, which is the usual Laplacian in only one direction and this vector field in another direction. So again, this is a hypoelliptic operator. That's easy to check, and the integral kernel, which determines the solutions of the heat equation, is always a C infinity function, and we'll say something more about that in a moment. But now let's just look at solutions of the heat equation. Oopsie, gotta get rid of this, I guess. There we go. Suppose we have a solution of that K heat equation, that funny heat equation. In order to get some sense of what's going on, let's study where the solution is concentrated. Let's define for any given time, t, the center of mass, just to be the center of mass of ut. It's easy to see that, for example, the fundamental solutions of this heat equation are always everywhere positive. So it's reasonable to look at their centers of mass in the usual way, the usual concept of center of mass. If you differentiate with respect to t, the formula for the center of mass, then you'll see right away that the x-coordinate of the derivative of the center of mass, or rather the derivative of the x-coordinate of the center of mass, is the y-coordinate of the center of mass. And as for the y-coordinate, there's no change whatsoever. The center of mass is stable as far as height above the x-axis is concerned, but it drifts according to the second term. And there wouldn't be any drift at all if you do the calculation if there wasn't this y ddx term. For the usual Laplacian, the usual heat equation, heat doesn't drift, it doesn't move, it just stays, it spreads out, but it spreads out isotropically. Here there's a sort of dynamical quality to the way that heat propagates. And so here's a little picture. You have some solution of the heat equation, maybe some initial solution on the left, and now you see how it propagates as time goes on, and it drifts over to the right if the solution is above the x-axis, and it drifts over to the left if the solution is below the x-axis. Okay, this is just a cartoon. The heat equation has infinite propagation, so instantly there's heat everywhere, but the bulk of the heat is propagating in the way that I've indicated in this picture. Okay. To make that, to exploit that in some reasonable way, let me point to just another little piece of I don't know, analysis here. It's a basic property of the heat operator, which follows from that rescaling argument that you saw earlier. That if you take two functions on a compact, let's say manifold, and I guess I've written here on the circle, you take two functions which are disjoint from one another, sigma 0 and sigma 1, and you ask yourself, to what extent does heat propagate from the support of sigma 0 to the support of sigma 1 over small times? And the answer is it doesn't propagate at all. This product of operators, this off-diagonal contribution to the heat operator e to the minus t delta, is vanishingly small. It goes to 0 like e to the minus 1 over t. However you measure the size, it always goes to 0. away from the diagonal, the integral kernel e to the minus t delta, as t goes to 0, converges in every possible way to 0. And the same thing is true for the Kolmogorov operator, and for that matter also for the hypoelliptic Laplacian. As long as you introduced a drift into the functions that you see above, the function sigma that you see above, I guess I'm now calling them phi. So if I have a function on the circle, let me build a drifted version of it, phi t, according to this formula. It means I'll show you a picture on the next slide what it means. If I can, now it's interesting. I shall try to, I see, good at this. Show you a picture, see, show you technical problems here, go away. How do I get this to? I shall, there, that will do the job. There we go. Sorry about that. So what I've drawn in red is a function on the circle, or the support of a function on the circle, which I've made into a function on the cylinder just by making it depend only on the circle variable. And now I've drifted it in the way that I described before. And the effect of that drifting is to shear the support of the function exactly as indicated in blue. And so the blue represents the support of a drifted version of a function supported in the red area. And then again, there's an easy estimate which says that the integral kernel for the L hypoelliptic Laplacian heat equation is concentrated exactly as you see it. The heat does propagate, so to speak, from the red region, but only to the blue region, to this sheared or twisted version of the diagonal. And what that means is that if you're interested in calculating a trace, if you're interested in integrating the integral kernel over the diagonal, then you're only going to get serious contributions where the red and the blue regions intersect, which I've colored in this tasteful, I don't even know what that is, green, something like that. Okay, and so the integral kernel for the hypoelliptic Laplacian, thanks to this standard concentration property, which now has a drifted component to it, the integral kernel actually concentrates in bands. Sorry, on the diagonal, the integral kernel concentrates in bands. If you're calculating the trace, you need to integrate e to the minus TLB, p comma p, over all of the cylinder. But in fact, the integral is going to be basically 0, except in bands, which depend on the value of t, and little t that is, and also on the value of b. As for what happens on those bands, you can do the same sort of rescaling argument that we discussed at the beginning, using, well, I guess that idea is initially adapted to proving the asymptotic law, but Ezra's methods apply here also, because there are some Clifford variables to rescale as well. And if you do it, it's rather interesting what happens. So the rescaling, like everything else, takes into account the drift term in the hypoelliptic Laplacian, and it's exactly as I've drawn in this picture and indicated in the formula. You stretch along the circle by a factor of b squared. You stretch vertically just by a factor of b, and I'm doing the stretching around some band bn, as you see here. And now you ask yourself, what does the hypoelliptic Laplacian look like if you transfer it using this diffeomorphism to the new manifold? And the answer is, it looks like in standard UV coordinates on the fat cylinder, it looks like what you see below. The first two terms are Kolmogorov's operator. And so to that extent, these operators LB are converging to a fixed final operator, which is Kolmogorov's operator. Then there's a 1/2 n squared. Well, that's fine. That tells you which geodesic band you're on. And then there's an awkward term, which is b squared n du. And remember, b is going to infinity, so we'll discuss that in a moment. And then there are some terms which are of order 1 over b. They come from taking the potential term in the hypoelliptic Laplacian, which was 1 over b squared y squared, and transforming it. And so these terms go to 0 as b goes to infinity, and I won't tell you what they are. They're not consequential. Yeah. But the term that's in red is consequential, and it would be a problem, except for the fact that, first of all, it commutes with all of the other terms in the expression for LB. It commutes with LB. And not only that, it exponentiates to 1, because on the right-hand side, we're working on a cylinder of radius b squared. So this is a certain vector field on the cylinder, but b squared e to the minus b squared n du is exactly a flow which moves exactly once around the cylinder. The exponential is 1. So you can forget about that bad term. That's another rather beautiful discovery of Bismut. This term, which has no chance of being well behaved as far as the operator is concerned, is completely inconsequential when you look at the exponential. So in that respect, it's a little more involved than what happens for the Dirac operator, where this extra term doesn't enter into play. All right, and so now you can forget about it. You see that as b gets really, really big, you can do the calculation of what is e to the minus TLB just by looking at Kolmogorov's operator. As b gets really, really big, this cylinder of radius circumference b squared eventually becomes a plane. And so the operator k that I've written here is actually the Kolmogorov operator on a plane, on the UV plane. It should be minus du squared plus u dv, not y dv, of course. And there is an e to the minus n squared over 2t there, because there's a 1/2 n squared appearing in the formula for LB. There's an extra b that occurs when you study these additional terms in the matricial version of the hypoelliptic Laplacian. But that b conveniently cancels with the b that you see. Maybe I'll just write here. There's going to be some change of variables when you integrate over w, and that b conveniently takes care of those. All right. And you arrive at the following conclusion, if I can train myself to operate these slides properly. Well, maybe before that, one of the things that Kolmogorov did was he actually worked out what the integral kernel was of this operator, just like Mailer actually worked out what the integral kernel of the harmonic oscillator is. And here's what it is. It's kind of a mess, but at least it's Gaussian. It's not too messy. And of course, we're only going to use this on the diagonal. So you can forget about the u terms, and you can more or less forget about the v terms. You just have to worry about where v1 gets added to v2 in the second term of this crazy expression. So you can use this explicit formula, and what comes out of it is the following thing. To calculate the supertrace of e to the minus TLB, we have to integrate the integral kernel over the diagonal. That integration only involves integrating near each, so to speak, geodesic band, because outside of those bands, the contribution to the integral is exponentially small. If you calculate within each band, you can use the rescaling argument, the one I just did, and you see that what's involved is just some explicit integral involving Kolmogorov's operator, as I explained. And I did the change of variables here that I was fussing about on the previous slide. And now you just have to do this integral, which is a Gaussian integral, and out comes the explicit formula, which is the Selberg trace formula, so to speak, in the case of the circle. This is the right-hand side of that formula with which we began. So the various stages which are involved here involve some interesting surprises that you don't see in ordinary index theory. This new matrix algebra that we saw early on, which I used to justify the definition of LB, and then some interesting new dynamical considerations towards the end as you attempt to evaluate the, if you like, small time or large B asymptotics of the integral kernel. And it's time to stop. Thank you very much.
Well, thanks very much. Thanks for this very nice talk. And do we have any questions now? Marco?
Hi, Nigel. Thank you. That was a great talk. One thing that I'm trying to understand is that in taking this heat operator and in forming this this replacement for it, which involves the S1 cross R and involves taking this exterior algebra and this Dirac operator and so on. One of the ingredients that you needed in order to make it work was the constant Dirac operator. Am I getting that right?
Yes, that's correct.
Okay, and so does this mean that that this theory works well for homogeneous spaces, or what
Yeah.
can you directly generalize what you'd explained to us to?
You can directly directly generalize what I explained to any Riemannian symmetric space, a G mod K. The generalization involves one extra step, which I didn't mention, and it has to do with the fact that the Constance operator on a non-compact group is not elliptic, and so there's some additional problem that has to be overcome, which is a significant problem.
It can be, but it can be done.
It can be done, and one obtains explicit formulas. The final conclusion is that there is, thanks to Bismut, an explicit formula for any semi-simple orbital integral associated to any real reductive group. And what are you calculating here? You're evaluating the orbital integral on the integral kernel of the Laplacian, or indeed basically anything. You can multiply the Laplacian, e to the minus Laplacian, e to the minus Casimir. You can multiply it by anything in the center of the enveloping algebra. That's the final formula. You get enough instances of computations of these orbital integrals basically to characterize what the orbital integrals are. And for example, to go back to what I was saying at the beginning, basically to determine the Planche-Turrell formula. I think that it's not necessarily literally true, but it's pretty close to being true.
And when you do it in this more general case, what is the extra direction that you need to add? I mean, is it only...
Oh, yeah, I should have, yes, thank you. That's certainly worth saying that. For a compact group, it's exactly what I did mention, which is the group times the Lie algebra. For a non-compact group, what you work on is you take the group times the Lie algebra, but then you divide the whole thing by K. So it's the group times the Lie algebra divided by K. So it's a bundle of copies of the Lie algebra of G over G mod K. Well, it's of course a trivial bundle, but it's a bundle.
And the exterior algebra would be on that bundle? Would be?
Indeed, the vector bundle in question is the exterior algebra bundle. The exterior has fibers, the exterior algebra of G. In order to obtain more interesting formulas for geometry and also for representation theory, you can also tensor in with any G-covariant line bundle on G mod K. So you can add any representation of K to the story, which I suppressed throughout the discussion.
Okay, thank you.
Hi, Nigel.
Hi.
So I have a rather naive question. So this is a new construction in index theory, but would there be some also a counterpart, infinitesimal counterpart in mechanics, or whatever, or in symplectic geometry, or whatever you get from it? So where you dequantize and you would, or I know Jean-Michel or whatever, like would discover new extension of Hamiltonian mechanics in that way, or not really?
I mean, certainly, the most honest answer is I don't know, but I would like to think that the route that Jean-Michel takes to these orbital integrals and to some beautiful formulas, and for example in representation theory, I'd like to think that they in the end they will not involve the mountain of analysis that they currently do involve, and that we'll understand much better geometrically what's going on. It's not exactly an answer to your question, but I believe eventually there will be a presentation of exactly these ideas, which is more geometric and less analytic. As for whether you can take some, I don't know, semi-classical limit of all of this, I guess I don't have the expertise to answer that. It's very hard to, I mean, this is very close to representation theory, as I tried to suggest. And you might ask, what does Harish-Chandra's Planche-Turrell formula mean, classically? What's its classical counterpart? For me, that's a very hard question. I don't know the answer to that. And that would seem to be just a piece of this story here.
Okay, thank you.
There's a question by Yang Liu.
Hi, Nigel. Hi. Thanks for the great talk. So I'm wondering for this parameter B, right? So is there, so you kind of, this taken limit process is sort of signing grades. Like, is there like a sort of a framework of a symbol calculus so that this sort of take the Fourier transform picture, right, to the symbol side to compute the limit of B? Is that somehow a approach or some work on that direction? So yeah.
That's makes me think of efforts on the non-commutative geometry side of people like Omar Mohsen and Eric van Erp and Bob Youngkin, who are indeed trying to understand operators like this from a pseudo-differential point of view. It's very hard to think of this operator as being elliptic in some calculus. So I don't know to what extent it's going to be ultimately possible to symbolify this whole discussion. So this, I don't know how to think of LB as being actually elliptic in some useful calculus. And I have a feeling you'd need to answer that properly before you could do what you're saying, make everything, do all of this work at the level of symbols.
Thank you.
But we'll see. At the moment, it doesn't exist.
There's a question from Gunnar.
Yeah, hi. I have maybe a silly question, but in the middle of your talk, you somewhere said that the Dirac operator associated to the LB Laplacian acts on differential forms. Is it somewhere possible to let it act on classical spinors, or?
Well, I guess the answer is it's certainly possible. You could just take the, is it possible? Maybe it's not possible. When you build the operator Q, which is an integral part of the construction, of course you use, in higher dimensions, you use Clifford matrices, which you didn't see because I only did it in one dimension. But in fact, you use the two possible sets of, both of the two possible sets of Clifford matrices, which act on the exterior algebra. So the endomorphisms of the Clifford algebra are made up of two copies, sorry, the endomorphisms of the exterior algebra are made up of two copies of the Clifford algebra. And both of those get used in the definition of the operator Q. So it's not obvious how you would make Q act on anything smaller than the exterior algebra. So, yeah,
Thanks.
It may be possible, but I don't know how to do it.
Right, any further questions?
Well, Eckhard, maybe I can give.
Jean-Michel, yeah, I was wondering.
I've given several talks like this, and Jean-Michel always shows up to. Yeah, I'm glad I didn't know you were there. But go ahead.
Yes. So maybe on the final question, I think that from the point of view of quantization, what makes these operators a bit strange is that quantization is connected with, let's say, symplectic transformations. And in this precise case, what we quantize are not real symplectic transformations. They are imaginary symplectic transformations, which means that the usual consequences of quantization become a bit strange. And otherwise, you could really, strictly speaking, say that you can do this quantization using the fact that there is a group theory structure, which means that in general, while in general quantizing imaginary symplectic transformations is impossible, in the context of group theory, you can do that. And that's exactly what happens from the point of view of quantum mechanics. Yeah, that's a very short brief, maybe. Yeah.
Okay, thanks very much. But since Jean-Michel is here, can you maybe tell us how you actually did come up with the hypoelliptic Laplacian?
Oh, yes. So the original idea was to try extending the idea of the Witten deformation to the loop space of a manifold, where as a Morse function, you would use the energy of the given loop. The interest for this is that the critical points of those are the closed geodesics. Now, obviously, if you try to do this on the loop space itself, you end up having a lot of analytic difficulties, which are well known. I mean, some of them might be progressively solved now, but at the time it was just totally unthinkable. And so in effect, this Witten deformation, as far as I know, on the loop space itself does not exist. But so what I try to do is to say the following: even if it does not exist, let's try to take a semi-classical limit of this Witten deformation. That is, let's look at it, but on a very small time interval, right? So if you have the Witten deformation, you have the heat kernel on the loop space, and you can try to make the time of propagation in the loop space very small. So if you do that, then things tend to localize on the original manifold. And if you believe that the Witten deformation exists, there is a semi-classical aspect of this Witten deformation which should exist. But now you see the original Witten deformation does not, but the semi-classical limit has a chance of existing. And so if you interpret things properly, what you observe at the level of this hypoelliptic Laplacian is just a semi-classical shadow of the non-existing Witten deformation. Okay, so that's literally this. That's one aspect of it. Okay, you have an object which does not exist, you take its proper limit. Now we are back on the original space, and you find that in effect, the Witten deformation ultimately exists and does for you, in some sense, exactly what the Witten deformation is supposed to do. Witten deformation is supposed to interpolate between Hodge theory and Morse theory. And in this case, at the semi-classical limit, what it does, it interpolates between classical Hodge theory, not the Hodge theory of the loop space, but the Hodge theory of the manifold, and not the Morse theory of the energy functional, but simply the generator of the geodesic flow, which for all practical matters is the same thing. Now, I gave you the Morse theoretic aspect interpretation. There is another aspect that Nigel has touched upon in the context of group theory, and this is connected with localization formulas in equivariant cohomology, where you do in effect do Doistermaat-Heckman localization, but now where the considered space is the orbit space for the loop group. And so that's an infinite dimensional version of Doistermaat-Heckman localization. And so literally speaking, what Nigel has described, I mean, or what I did in the context of compact Lie groups can literally described as an infinite dimensional version of Doistermaat-Heckman formula. The added thing in the context of non-compact Lie groups is that you have these extra difficulties that you have to deal with non-Riemannian manifold, non-compact orbit spaces, and so on. But ultimately, there is a happy end.
Okay, yeah, thanks a lot. So do we have any further questions? Well, if it's not the case, then let's thank Nigel again for this wonderful talk.
Very much.
Yeah, and see you next week.
Bye-bye.
Don't disconnect.
So yeah, so many of you perhaps would like to stick around for a few minutes because we're closing our Junior Global Poisson workshop tonight in the next few minutes. So and there's a few awards for best contribution that we want to award to some of our junior participants. Perhaps I could start with that if there are no more. Yeah. Okay. So let me share a slide. Right. So just to confirm, everything is visible. The whole slide is visible to everyone. Is
yes.
That
yes.
Yeah. Okay. So okay. So as I just mentioned, we're closing the Junior Global Poisson workshop. This is the second time we've done it. So first of all, I want to mention that so there were 4 of us in the organizing team. We had 2 incoming younger members of our team who were Leonard Stockenschmidt and Elia Gayur, who were instrumental in making the conference work as well as it did. The next thing that I want to mention is that we applied this time to get some funding in order to support some awards for best contribution. We were successful, so we got some funding from the University of Sheffield through the so-called Think Ahead program. So there's 4 awards, and 2 of them go to PhD students, current PhD students, and 2 of them go to postdoctoral fellows. The awards are for presentation skills. So we judged things like clarity, engagement, delivery. The award panel consisted of 3 people, so Francis Bischoff, Anastasia Matveyeva, and myself. So I want to emphasize that the awards are for presentation skills. They're sort of not to be interpreted as a reflection on the mathematical content, because of course we don't want to pretend like we have enough competence to have to be able to pass judgment on that. So, we somehow one of the main purposes of Junior Global Poisson is to create a space for junior participants to grow. And one of the main points that we want to emphasize is that presenting your research in a coherent and complete and confident manner is an extremely important part of a career in academia. Okay, so having said all that, without further ado, let me announce the 4 winners of the award. So in no particular order, the first award goes to Caroline van Gerst from the University of Sheffield for her talk, Frobenius manifolds, mirror symmetry, and integrable systems. So let's give her a round of applause. The second award goes to Friedrich Wallach from Imperial College London for his talk on a generalization of Lie and Courant algebras and its applications to exceptional generalized geometry. So let's give Friedrich a warm round of applause. The third award goes to Stefan Goerdens from KU Leuven for his talk called the Poisson saturation of regular submanifolds. So let's give Stefan a warm round of applause. And last but by no means least, the award goes to Joseph Palmer from University of Illinois Urbana-Champaign for his talk Hamiltonian S1 spaces, symmetric integrable systems, and hyperbolic singularities. So let's give Joseph a warm round of applause. So all the awards come with a financial prize valued at £150, which will, in the next few days, we'll have to figure out exactly how to deal with. But let's give all the award winners and altogether all the junior speakers, many of whom presented absolutely exceptionally good presentations. Let's give them all one last round of applause. Thank you, that's it from me.
Well, maybe we should also give an applause to the organizers, right? So thanks a lot for thinking of doing again Junior Global Poisson. We hope that the tradition will continue, and hopefully in the fall you will decide to do it again. So thanks a lot for the organizers and participants. Thank you.
Thanks a lot.
Well, thanks a lot, and hope to see you next week. So next week, just to remind you, if I'm not mistaken, that's the Eastern Hemisphere schedule. Is
That's
it right?
correct. Yeah. That's correct. Yeah.
Okay. So thank you again, and see you.
Thanks, everyone.